Hello everybody, my name is Alejandro Pardo and I'm happy to present to you my work done at Qualitative University of Science and Technology KAUST in collaboration with Adobe Research, RefineLoc. So RefineLoc aims to solve the action localization problem, which is basically given an on-stream video, you want to localize the start and end points of every instance of an action in the video. People have been trying to solve this by using fully supervised annotations, which require humans to annotate start and end points in every instance in the video. However, this is very expensive. To solve this, we are trying to solve the same task by using only video level labels at training time. In this example, the action is surfing, and we try to localize each of the instances. However, at training time, we don't have the start and end points. To solve this, we propose RefineLoc that uses background-foreground information to generate pseudo labels that are going to refine the localization based on knowledge acquired previously. This is the overall architecture of RefineLoc. It is composed by three main modules, which is the feature extraction module, the quickly supervised temporal action localization based model or WSTAL based model, and the iterative refinement process. The backbone instructs snippet features of 2048 dimensions, and it uses TSN and I3D architectures with 15 and 16 frame snippets respectively. Our WSTAL module is composed by several submodules. The first one is the video snippet classification module, which aims to classify each snippet as a class of video. The second one is the foreground background attention module, which aims to classify each snippet as a background or foreground, depending on whether they belong to an action or not. The third one is the video label prediction module, which combines the output of the two previous to output a label for the whole video. Finally, the action segment prediction module combines the output of the first two modules and generate a prediction that is going to be used in the iterative refinement. Given our base model, we are going to generate pseudo ground truth in the iteration 0 to supervise the next iteration by using this pseudo ground truth. However, we explore as well what is the best way to generate pseudo ground truth by doing it with 5 different ways. The total loss that RefineLoc optimizes is the video label loss and a pseudo ground truth loss, with a beta parameter that puts the weight or the importance to the pseudo ground truth loss. We perform our experiments on ACTIVITYNET and Fumus to widely use datasets for this task. On ACTIVITYNET, we are the state of the art using TSN features, and we are very competitive by using I3D, only being beaten by BASnet. On Fumus, we are very competitive with all the methods of the state of the art, using both TSN and I3D. Our Ablation studies show that the best way to generate pseudo ground truth for this task is using the segment prediction, and the best beta for our loss is 4. The table below shows that RefineLoc's key component is the iterative refinement. It improves from 9 to 23 on ACTIVITYNET only using 3 iterations. Given that our method's key component is the iterative refinement, we wanted to apply it using different attention-based method. For that, we reproduce numbers of different attention-based methods, and we build on top their code RefineLoc's iterative refinement. These two tables show the results when applied to the WSTAL and BASnet. When applied to BASnet code, we are able to improve BASnet by a good margin, giving us the state-of-the-art in Fumus. This shows as well that RefineLoc is not only specific for this base model that we created, but is also generalizable to use in any other attention-based method. Qualitative results, in which RefineLoc is actually able to change predictions over the iterations. In the first example, it's actually beneficial for the metric, but in the second, it's not. This was RefineLoc. Please feel free to visit us in the Q&A session. Our paper ID is 706.